So in this learning module, we're going to look at two important visualizations, the histogram and the run chart. And as I mentioned beforehand, we talked about summary statistics in learning module 1. Those are good ways to come up with a single number that describes some attribute of a data set. But visualizations are always going to be more powerful because they're going to give us a way to kind of describe the entire characteristics of the data set within a single image. So the first visualization that I want to make sure everyone is familiar with is a histogram. So let's kind of take the example on the right here. Imagine you went out to some field and the field was a cherry farm. And naturally you would expect that there would be some variability in the height of the cherry trees. Maybe they were planted at different times. Maybe they have different exposure to sun or water. Maybe they just have different genetics. There would just be expected that there would be some variability in their heights. And say you went around and you measured the height of every tree and you wrote it down in a list. Naturally, you would have a data set there, and you can compute the mean value or the median that would tell you on average how tall you would expect the trees to be. You could compute a measure of dispersion like standard deviation or the interquartile range that would tell you how much variability there is in height around that central value. But if you really wanted to give someone a picture of the entire distribution or range of values that the height of those trees takes on, what you would probably want to do is use a histogram. And the way that you would do that is say, for example, that these are all very tall trees. I don't even think trees are really this tall. I took this image from the web, particularly cherry trees. At least where I grew up outside of Cleveland, cherry trees were not 70 feet tall. Anyways, you could go to your data set and you could kind of, now if you think about it, they're probably going to be very continuously varying. And what that means is you might have a height of like 62.4 and you might have a height of 64.7. So kind of the first thing you might want to do in order to facilitate some kind of summarization is to put them into bins. You might say, okay, I'm going to divide these. I'm going to count how many trees I have between 60 and 65 feet tall. And I'll count how many I have between 65 and 70 feet tall. And naturally, you can probably see how you would pick the lower and upper bound of your binning, but you might not understand how you would pick the bin width. And this isn't a stats class, so we're not going to worry about that. Just know you generally pick it such that you have at least a sample or two in every bin. And where you tend to have the most samples, that you have some kind of natural variability like this. And the way I just described that doesn't make a lot of sense, but I shouldn't have even tried to do it. Just for now, notice that the bin width in the majority of the software that we use will be determined by the software itself. But here, we're using a bin width of 5, so we count that there's 3 trees between 60 and 65 feet tall, 3 trees between 65 and 70, looks like 8 trees between 70 and 75. And if we graph that in what looks like a little bit of a bar graph, what technically we would be making is a histogram. And the way that we would interpret the histogram is the value on the y-axis would be how frequently values within the range given by the bin width on the x-axis occur in the data set. So in our data set, if we wanted to find the total number of values, we could just add all these heights up. And if we wanted to find how many were in a range, we could just pick a particular range. For example, here 10, there are 10 trees between 75 and 80 feet within our data set. So you can generate a histogram either in MATLAB using the histogram function or in Excel using the statistic chart family. And I'll show you how to do that. So in addition to kind of a histogram, another chart that as engineers you want to be familiar with is a run chart. And this is useful when you have data that's actually generated in a sequence or in time. And you're trying to visualize how that data kind of changes over time, particularly if there's some expectation that data would remain relatively constant. And these are really important as you would think in a manufacturing environment where the characteristics of your product should be the same all the time. And if you have variability in any of those characteristics, it's a cause for concern. So if you've heard of the term statistical process control or Six Sigma or something like that, these type of graphs are used very heavily within that field of study. So if you notice here, I'm just taking my data as it occurs. Particularly, we're talking about the errors that occur in some kind of process per month. And each month, I'm just plotting it on a graph, and I'm kind of drawing a line graph. In January, I had, I don't know, it looks like 75 errors. In February, I had 70 errors. In March, I had 68 errors. And if you think about what this allows us to do, it allows us to see trends in the data over time. I can see that my errors were trending down. That's probably a good thing. All of a sudden, they ramp up here starting in May. In addition to being able to see the trends in the data, if I overlay some additional plots on this graph, particularly a line that describes the central tendency of the data, along with some lines that maybe describe some bounds that I wouldn't expect the data would go outside, I can both see how far my data is away from the typical or average value by looking at comparing the trend to the actual teal line here. But in addition, I can have immediate visualization when data goes outside of my allowable range. And in a typical run chart, you don't have these horizontal lines. This is actually more of a statistical process control chart that you would use in Six Sigma. UCL and LCL are acronyms for upper control limit and lower control limit. So usually when data goes outside of those limits, we say the process is out of control. And as you may have guessed, the way you usually get those limits, if you were in a manufacturing environment, is you would go and you would control everything the best that you can. You would get everything just set up perfect. And naturally, there would still be some variability, but you would measure it. And you would quantify that variability using a measure of dispersion, like say, for example, the standard deviation. And you might say, okay, I expect that there's going to be some natural variation in my process. I have a measure of the standard deviation, and I'm only going to be concerned when the values go outside of plus or minus 3 standard deviations, where that standard deviation was measured kind of in the best case scenario. And that kind of ideal is known as what's known as Six Sigma. That's where that's coming from. S is the abbreviation for standard deviation of a sample, but sigma is actually the parameter that's used to describe the standard deviation of a Gaussian distribution. So you can go into this in a lot more detail, but just know that a run chart is going to give you some additional insight into data that's generated in time. Particularly, it will allow you to see trends, and it will allow you to know when the dispersion of the data set is increasing beyond typical levels. So I wanted to show you an example of how to do this in both MATLAB and Excel. We want to download that spring constant data, which we already downloaded, and we want to generate basic histograms and run charts in both MATLAB and Excel. So I have that data set here in my workspace. It's K. So if I want to plot the histogram, I just use the histogram function and pass in the vector that contains the data I want the histogram of. And there we see our histogram. And we can put labels on this if we want, but on the x-axis, we have ranges of the spring constant. For example, here, the bin values are from 1.8 to 2. And what this means is there are 64 springs that were manufactured with a spring constant between 1.8 and 2. In a similar fashion, there were 52 with a spring constant between 2 and 2.2. So that's how we interpret this histogram. If you want to do a run chart, the easiest way to do it in MATLAB is just to plot it and only pass in a single argument. And what you can see is if we were kind of just visually to look at the central tendency measure around 2, for the first 100 units that we manufacture, yeah, there's some natural variability, but something happens at unit 100 that's causing the dispersion in this data to increase dramatically. So if you notice, that's something you didn't see in the histogram. These are the same data sets. And when you look at the histogram, it just looks like, okay, yeah, pretty normal variation around my kind of average value of 2. But when you look at these in a run chart, you're actually, it would help to actually plot a run chart. You're able to see the point in time for which the dispersion increased. So that's the real value of the run chart in this case. If you have all the values in Excel, just highlight them all. That's the easiest way to do it. And once you got them all, go over to Insert Graph. The easiest way to plot a run chart is just to use the upper left 2D line chart, and you get that same graph that we had beforehand. You see there's natural variability around 2, but somewhere around 100, that variability increases. In addition, if you wanted to plot a histogram in Excel, you use the statistics chart family, which is here in the middle, and you just take the upper left option, which will allow you to generate a histogram. So you can play and clean these up, and the easiest way is not for me to show you how to do it, but for you to get some experience doing it yourself. It will stick better if you do it that way, and you'll have a chance to do that on the homework.